When you see the full moon blazing in the night sky, your intuition says it must be highly reflective. A bright, shining surface. And relative to the darkness around it, that's true. But the moon's albedo, its actual reflectivity as a fraction of incoming light, is only about 0.12. That means it reflects just 12% of the sunlight that hits it. It absorbs the other 88%. For comparison, freshly fallen snow has an albedo of around 0.9. If the moon were made of snow, it would appear nearly 8 times brighter in the sky. The absorbed sunlight doesn't disappear. It becomes heat. It agitates the atomic lattice of the regolith, creating lattice vibrations called phonons, quantized units of vibrational energy. This is why the lunar surface temperature swings from roughly 127 degrees Celsius in sunlight to minus 173 degrees Celsius in darkness. The moon is an efficient heat absorber, and quantum mechanics is responsible for that inefficient reflection through the energy level structure of its surface atoms. When sunlight is absorbed by the moon and converted into heat, the process is profoundly quantum mechanical. The energy does not simply flow into the rock like water into a sponge. It enters as discrete packets, photons, and it is stored and transported as discrete packets too, called phonons. A phonon is the quantum of vibrational energy in a crystal lattice. Just as a photon is the smallest possible unit of light, a phonon is the smallest possible unit of lattice vibration in a solid material. The moon's interior, from its regolith crust to its iron core, is threaded with trillions upon trillions of phonons, quantized ripples of atomic motion propagating through its bulk. The extraordinary temperature gradient across the moon, from scorching surface to the deep cold of its permanent shadow craters, is maintained and shaped by the behavior of these quantum vibrations. Every moonrise and moonset is accompanied by a slow quantum breathing of the regolith, absorbing and releasing phonons in tune with the rising and setting sun. If you split moonlight through a spectrograph, a device that separates light into its constituent wavelengths, you don't see a smooth rainbow. You see a rainbow interrupted by dark lines. These are Fraunhofer absorption lines, and they are a direct quantum signature of the atoms in the moon's crust. When sunlight passes through the thin but present sodium cloud around the moon, and when photons interact with the specific elements in the lunar regolith, photons of very precise energies are absorbed. An iron atom will absorb photons at exactly the wavelengths that correspond to the energy gaps between its electron orbitals, not approximately but exactly, to extraordinary precision. Each element has a unique set of energy levels, which means each element has a unique pattern of absorption lines. By reading the dark lines in moonlight, astronomers can remotely determine the chemical composition of the moon's surface without ever landing on it. The moon broadcasts its atomic identity through quantum mechanics every night. Here's the question that broke classical physics and launched the quantum revolution. Is light a wave, or is it a particle? The answer, discovered through painful decades of experiment and argument, is both. Simultaneously, depending on how you measure it. This is wave-particle duality, one of the central mysteries of quantum mechanics. The silver glow of a full moon hitting your retina is not simply a gentle wave of electromagnetic radiation. It is also a stream of discrete photon particles, each carrying a specific quantum of energy given by Planck's constant multiplied by the frequency of the light. These photons arrive at your eye one at a time. They are absorbed by individual molecules. They trigger individual chemical reactions. And yet the overall pattern of moonlight, its color, its intensity, its distribution across the sky, is perfectly described by wave mathematics. The moon does not send you a wave. It sends you a blizzard of particles whose statistics perfectly mimic a wave. Physics is strange. As moonlight travels the roughly 384,400 kilometers from the moon to Earth, something mathematically beautiful happens. The photons spread out. Not randomly, perfectly, according to the inverse square law. The intensity of moonlight decreases in proportion to the square of the distance from its source. Double the distance, quarter the brightness. Triple the distance, 1/9 the brightness. But from a quantum mechanical perspective, this is not just a classical geometry problem. It is a statement about probability density. Each photon leaving the moon's surface is described by a quantum wave function that spreads outward in a sphere. The further a point in space is from the moon, the lower the probability of finding a photon at that precise location at any given moment. Earth intercepts only an infinitesimally thin shell of that expanding sphere. The photons that enter your eye tonight are the ones whose probability wave happened to collapse at your exact location on Earth. Out of all the possible places in the solar system they could have ended up. Your eye is not a passive receiver of light. It is one of the most sophisticated quantum detectors in the known universe. The rod cells in your retina, responsible for low-light vision, contain a molecule called rhodopsin. Rhodopsin has a section called the retinal chromophore, a conjugated chain of carbon atoms whose electron configuration can exist in two geometric isomers, the 11-cis form and the all-trans form. When a single photon of the right energy strikes this molecule, it triggers an isomerization, a quantum mechanical rearrangement of the electron configuration that causes the chromophore to change shape. This is a photochemical quantum event. One photon, one molecular switch. Under a full moon, your rod cells are receiving somewhere in the range of 100,000 photons per second. Each one triggers its own individual quantum event. Each one is individually measured. The cascade of signals from these millions of molecular quantum detectors is what your brain synthesizes into the experience of moonlight. How sensitive is the human eye to light? The answer will stun you. Under ideal dark-adapted conditions, the human eye can detect as few as 5 to 7 photons hitting the retina simultaneously. Some experiments suggest single photon sensitivity is achievable under the right circumstances. This means your visual system is operating at the absolute quantum limit of what is physically possible. You cannot build a more sensitive light detector without violating quantum mechanics itself. The full moon provides roughly 1,000 lux of illumination on Earth's surface, bright enough to read by, bright enough to cast shadows. Under these conditions, your photoreceptors are comfortably saturated and your cone cells, responsible for color vision, are fully activated. But at the threshold of vision in the dimmest moonlight, individual quantum events in individual rhodopsin molecules are separating what you see from what you don't. Your perception of the night sky is literally shaped by quantum measurement events at the molecular scale. Louis de Broglie proposed one of the most audacious ideas in physics. Not just light, but everything, matter itself, has a wave nature. The de Broglie wavelength of an object is given by Planck's constant divided by the object's momentum. For an electron, this wavelength is large enough to be measurable and to produce interference patterns in experiments. For a baseball, the wavelength is absurdly small, far smaller than any atom, completely unmeasurable. For the moon, with a mass of roughly 7.35 times 10 to the power of 22 kilograms, the de Broglie wavelength is so vanishingly small it makes a proton look enormous. In principle, the moon has a quantum wave nature. In practice, its wave properties are so compressed that they will never produce any observable quantum interference in any conceivable experiment. And yet the principle holds. The moon is, in the most rigorous theoretical sense, a quantum object, just an extremely well-decohered one. Before moonlight can exist, sunlight must. And before sunlight can exist, the sun must shine. At the heart of the sun, in a region so hot and dense that matter exists in states we have no everyday analogy for, hydrogen nuclei, protons, are being fused together to form helium. This fusion releases the energy that ultimately becomes the photons that cross space, strike the moon, and bounce into your eye as moonlight. But there is a deep puzzle at the heart of solar fusion. The sun is not actually hot enough for fusion to happen. The core temperature of the sun is approximately 15 million degrees Celsius. Sounds extraordinary. But for protons to fuse through classical means, colliding hard enough to overcome their mutual electromagnetic repulsion, the Coulomb barrier, the temperature would need to be roughly 1,000 times higher, on the order of 10 billion degrees. The sun should not shine. And yet it blazes. The answer lies deep in quantum mechanics. Quantum tunneling is the phenomenon by which a particle passes through an energy barrier that it classically should not have enough energy to overcome. Imagine rolling a ball up a hill. Classically, if the ball doesn't have enough energy to reach the top, it rolls back down, it cannot get through. But in quantum mechanics, particles are described by wave functions, and wave functions do not simply stop at a barrier. They decay exponentially into the barrier and, if the barrier is thin enough, emerge on the other side. The particle has, in a sense, passed through the hill without going over it. This is not a metaphor or an approximation. It is experimentally verified, essential to the operation of transistors, scanning, tunneling microscopes, and nuclear processes. In the sun's core, two protons approaching each other face the Coulomb barrier, their positive charges repelling each other with enormous force. But quantum tunneling allows them to pass through that barrier anyway, fusing together and releasing energy. Every photon in moonlight was born from a quantum tunneling event. Let the implication of quantum tunneling fully sink in. Without tunneling, protons in the sun's core could not fuse. Without fusion, the sun would not shine. Without sunlight, the moon would be invisible, a dark rock orbiting a dark star in a dark universe. Without the sun's energy flowing to Earth, the chemistry of life would be impossible. Photosynthesis, which powers the base of virtually every food chain on Earth, is driven by sunlight. The warmth that keeps liquid water on Earth's surface requires the sun. The oxygen in your lungs, the carbon in your cells, the calcium in your bones, all of it traces back, through chains of nuclear and chemical reactions, to stars that burn because of quantum tunneling. You exist because quantum mechanics permits particles to do the impossible. The moonlight falling on you tonight is a reminder, written in photons, that the universe runs on rules that defy classical intuition, and that those rules made everything possible. The proton-proton chain is the nuclear reaction sequence that powers the sun. It begins when two protons tunnel through the Coulomb barrier and fuse. One of them undergoes beta plus decay. A proton converts to a neutron by emitting a positron and a neutrino. This creates a deuterium nucleus. A second proton then fuses with the deuterium to create helium-3. Finally, two helium-3 nuclei fuse to create helium-4 and release two protons. The net result, 4 hydrogen nuclei become one helium-4 nucleus, and the tiny difference in mass is released as energy, gamma-ray photons and neutrinos. Those gamma-ray photons begin a random walk through the sun's interior that takes, on average, somewhere between 10,000 and 100,000 years before they reach the surface and escape as visible light. The photons of moonlight you see tonight may have been generated by quantum tunneling events that happened before humans learned to write. Ancient quantum events are illuminating your face right now. Inside the proton-proton chain, one of the fusion steps involves beta plus decay, a phenomenon governed by the weak nuclear force. A proton converts into a neutron by emitting a positron, the antimatter counterpart of an electron, and an electron neutrino. This is a quantum event involving the W boson, one of the force carrier particles of the weak interaction. The W boson is extraordinarily massive relative to other force carriers, about 80 times the mass of a proton, and exists for only a tiny fraction of a second before decaying. Yet this momentary particle, this fleeting quantum event, is what allows the sun to turn hydrogen into helium and is therefore responsible for every photon of sunlight and every photon of moonlight. The weak force is literally one of the reasons the moon shines. The fundamental forces of nature, the quantum forces, the particle physics forces, are not abstract academic curiosities. They are the engines of the cosmos, and they are running constantly, invisibly, all around you.